In this video, I'm going to be discussing the three major acid-base theories that you'll encounter in your first year of chemistry. So there are three theories present, the first of which is Arrhenius. There's also Bronsted-Lowry and Lewis. So I'm going to start by talking about Arrhenius. An Arrhenius acid is defined as an acid or any kind of compound that dissociates in water to form H plus ions. To form H plus. An Arrhenius base, on the other hand, put an A here for acid, I'll put a B here for base, is something that pretty much does the exact same thing, except instead of forming H plus ions, it's going to form OH minus ions, or hydroxide ions. So that's all an Arrhenius acid base is. It's the simplest one to know and to recognize. An Arrhenius acid would be anything that starts with H, any chemical compound starting with H. So like HCl, H2SO4, so on and so forth. Whereas Arrhenius bases might be things like LiOH, NaOH, just ionic compounds containing the hydroxide anion. Next topic I want to talk to you about is Bronsted-Lowry acids and bases. Bronsted-Lowry acids are defined as H plus donors, whereas Bronsted-Lowry bases are defined as H plus acceptors. So let's see exactly what this means. In the case of a Bronsted-Lowry acid base, it's not always certain which one is the acid, which one is the base. So I'm going to give you an example of water. So water is a compound that is called amphoteric because it can function both as an acid and as a base. Here water is reacting with the acid HCl, while in a Bronsted-Lowry acid-base reaction, one compound donates the hydrogen and another compound accepts it. In this case, the water will be the base, the hydrochloric acid will be the acid. So what we end up getting is H3O plus and Cl minus. So what we can see is that the HCl going from here to here donated its H. It lost it because this hydrochloric acid gave it to the water. On the other hand, this H2O going from here to here, in fact, accepted a hydrogen. So therefore, this is your base of water. Your acid is HCl. Something else that's worth noting is on the other side of the equation, let's say we go back the other way. Well, if we go from right to left, this hydronium molecule would have donated to give you the H2O. So on this side, we say that H3O plus is our conjugate acid, and similarly, this chloride ion would accept an H plus to become HCl, so therefore we say it is our conjugate base. Let's show you next how water can act as a base. I'm sorry, how water can act as an acid. So let's say we have H2O and it's reacting with a strong base, something like Li. Well, actually, let me not pick that one. I'm going to just pick another compound here. Let's say we had it reacting with something like ammonium, NH3. Well, something that could happen here is the water could give its hydrogen to the ammonia to form an ammonium ion and an hydroxide OH minus. So what we can see here is this time water was actually giving away our H. It was donating it, so therefore water is our acid. On the other hand, ammonium was accepting a hydrogen, so it's our base. Again, going to the other side, our acid becomes our conjugate base, and our base becomes our conjugate acid. And that's pretty much how that works. I'm going to go ahead and just write out amphoteric over here. It's an important word that you'll probably encounter on a multiple choice question. And amphoteric just means a compound that can be both an acid or base. So I'm just going to abbreviate that here as both an acid and a base. So an amphoteric compound is one like water. Ammonium can do it too. Even things that are generally considered acids, like carboxylic acids, can function as bases in certain reactions. Final example I want to talk to you about is Lewis acids. Lewis acids and bases. So Lewis acids are defined as electron pair donors. No, electron pair acceptors. So your Lewis acids are your electron pair acceptors, and your Lewis bases are your electron pair donors. Let's show an example of that. So the typical one you'll see in your first year chemistry course looks like this. So this is NH3. This compound is ammonia, and it's reacting with boron. Boron's kind of odd because it doesn't satisfy the octet rule, and that's why it functions as such a great Lewis acid. Well, it kind of has an empty shell. It's capable of accepting 2 more electrons, and this nitrogen over here conveniently has 2 electrons on it, which can be donated to boron. And what we get is a reaction where these two come together. And we form this structure here. So that's how Lewis acids and bases work. In this case, our boron trihydride was functioning as the electron pair acceptor, and therefore was the Lewis acid. Our ammonium was functioning as the electron pair donor, and therefore was our Lewis base.